You've seen those big sci-fi starships crossing galaxies like it's nothing. But here's the straight reality. As a species, we have basically gone nowhere. In real physical distance, humans have never been far from Earth. And once you hear the numbers, it feels less like we're a spacefaring civilization and more like we're still standing right next to our front door. So start with the thing most people picture when they hear we went to space. You climb into a rocket, it launches, the sky turns dark, and around 62 miles up you cross what we call the edge of space. That line is called the Kármán line. 62 miles. If you drive that on a highway, it's a short trip, but on paper, congratulations, you're in space. Now look at the International Space Station, the main place where humans actually live off Earth. It orbits at roughly 250 miles above the surface. That's still a distance you could cover in a few hours by car. But in altitude, it sounds serious. A couple 100 miles straight up, the station circles the planet about once every 90 minutes, moving at around 17,500 miles per hour. 17,500 miles per hour sounds extreme, and compared to your normal life, it is. A typical airliner cruises around 500 to 600 miles per hour. The station is moving dozens of times faster than that. But compared to the real speed limit of the universe, the speed of light, it is tiny. At ISS speed, you are moving at about 26 millionths of light speed. That's 0.000026 of light speed, basically zero on the cosmic scale. So here's the first hard point. When we say we've been to space, we mostly mean we've gone a few hundred miles up and then gone around in circles again and again, still hugging the planet, which raises a simple question. Have we ever actually gone far in a way that matters for the size of the solar system? The obvious next step is the Moon, because that's the only place beyond low Earth orbit that humans have reached. You might assume that means we've broken away, gone properly out into space. The farthest any human has ever been from Earth was during Apollo 13. On that mission, the spacecraft swung around the far side of the Moon in a rescue trajectory. At the most distant point, the crew was about 248,000 miles from Earth. 248,000 miles sounds huge, and it is, compared to your daily life, but keep it in context. That distance is actually less than the total mileage many people put on a car over its entire lifetime. If you drive one car for a couple of decades, you can easily hit 200,000 miles or more. So the absolute distance record for any human being, the farthest anyone has ever been from home, is roughly the lifetime mileage of a well-used car pointed straight up. And here's the part that really matters. We hit that record in the early 1970s, and we have never pushed it farther. Every human mission since then has stayed in low Earth orbit, a few hundred miles up. We have better computers, better materials, better everything, but the maximum distance humans have travelled from Earth has not changed in over 50 years. So then you might say, fine, humans haven't gone that far. But what about our machines? Have we at least sent something truly far into space, something that actually starts to test the size of the solar system? That's where Voyager 1 comes in. Launched in 1977, it flew past Jupiter, then Saturn, and used their gravity to boost its speed. After that, it just kept going outward, decade after decade. Today, Voyager 1 is more than 15 or 16 billion miles away from the Sun. The exact number keeps increasing every second. Its speed is about 38,000 miles per hour relative to the Sun. That sounds like the definition of fast. You will never ride in anything that moves that quickly. But again, compare it to light. Voyager 1 is travelling at only about 0.006% of light speed. That is 6,000ths of 1%. If you tried to send Voyager 1 at that speed toward the nearest star, Proxima Centauri, it would take over 70,000 years to get there. That is longer than all of recorded human history. So even our best robotic explorer, moving far faster than any crewed spacecraft, is still painfully slow when you compare it to the distances between stars. And that leads to the next question. If that is our fast, how big is even just our own backyard, the solar system? To get a grip on that, you need one more basic unit, an astronomical unit, or AU. That's the average distance from Earth to the Sun, about 93 million miles. Earth sits at 1 AU, Mars is roughly 1.5 AU, Jupiter is around 5 astronomical units, Saturn is around 9 to 10 astronomical units, Pluto orbits way out, around 30 to 50 astronomical units depending on where it is in its stretched out path. Remember, each astronomical unit is 93 million miles, so by the time you talk about Pluto, you're already dealing with billions of miles from the Sun. Voyager 1 has gone beyond the orbital distance of Pluto. It is over 100 astronomical units away. That means tens of billions of miles. That sounds like an insane distance until you compare it to a single light year. That's the distance light travels in 1 year, roughly 5.88 trillion miles. So even after almost 50 years of flight, Voyager 1 has still covered only a tiny fraction of just 1 light year, and the nearest star is more than 4 light years away. Put all of this side by side, low Earth orbit at a couple hundred miles, the Moon at roughly 250,000 miles, Voyager at tens of billions of miles, a light year at trillions of miles, and you see the pattern. Everything we have done so far with people or with machines is extremely local. We are still right next to our own star, and that sets up the core question for this whole story, because distances on their own are just numbers. What matters for you is time. Your life has a fixed length. So here's the key problem. Given the physics we know, the rockets we can realistically build, and the limits of human biology, if you decided to dedicate your entire lifetime to going as far as possible, how far could you actually travel? How much of this enormous scale could one person cross before their clock runs out? To answer that, we have to stop thinking mainly in miles and start thinking in years, and accept that your main opponent in deep space is not distance by itself, it's your own lifespan. Before you even think about leaving Earth, you have to swallow one brutal fact. Out there, your main enemy is not aliens, not black holes, not explosions. It's your own lifespan. Your body's clock is the hard limit on how far you can personally go. And once you run the numbers, you see very fast that the universe doesn't care how brave you are. It just runs out the timer on you. So let's start simple. How many years do you actually have available for real travel? Not childhood, not retirement, just mission time. Let's be generous. Say you're space ready at 20, your body can handle launch, radiation, isolation, all of it, and you stay medically fit for extreme missions until about 80. That gives you roughly 60 years where you could, in theory, be flying somewhere. But even that number is fake, because you can't spend 60 years just flooring the accelerator in a straight line. In real missions, you have to accelerate up to speed, cruise, then slow down so you don't slam into your destination at lethal velocity. You also need time on the ground, time in training, time between missions, so right away your lifetime travel window shrinks. Maybe it's a few big missions adding up to 20 or 30 years actually in transit. Maybe it's one insane flagship mission that eats the last decades of your life. Either way, it's not infinite. And that sets up the key question. If you only get a few decades of real motion, and the clock is always ticking, what does that look like compared to the one thing you can never beat, the speed of light? Light sets the absolute speed limit in the universe. It moves at about 670 million miles per hour. That's not a dramatic line, that's the actual number. If you could somehow ride a beam of light, you'd go from Earth to the Moon in just over a second, to the Sun in a little over 8 minutes. The nearest star to us, Proxima Centauri, is about 4.24 light years away. Convert that to miles, and you're looking at roughly 25 trillion miles. Not billions, trillions. Now imagine you had a ship that could reach 10% of light speed. That's about 67 million miles per hour. No rocket we've ever built can do that with people. But just pretend. At that speed, the raw distance to Proxima Centauri takes a bit more than 42 years one way if you could instantly jump to that speed and instantly stop. But real physics doesn't let you do that. You have to ramp up and ramp down. So a realistic round trip with acceleration and braking phases eats over 40 years of your ship's internal time, probably more. That is basically your whole adult life, spent on one there and back. So here's the tension. Even at 10% of light speed, which is way beyond anything we can currently build, your lifetime barely stretches to one nearby star and back, and that's if everything works perfectly. So if that's what the dream looks like, what are we actually doing right now in the real world? Look at the fastest hardware we've ever flown. The champion is NASA's Parker Solar Probe, an uncrewed mission that dives close to the Sun. It's reached speeds of around 430,000 miles per hour at its closest approaches. That's insanely fast for a machine we built. But as a fraction of light speed, it's tiny, only about 0.064% of light speed, not even 1/10 of 1%. And that's with a very specialized, very extreme trajectory. Human missions are far slower, and most crewed spacecraft cruise well under 20,000 to 25,000 miles per hour relative to Earth. That's enough to reach orbit, reach the moon, move around the inner solar system, but it is not Starship fast. At those speeds, you're locked inside the solar system for your entire life, no matter how early you start or how healthy you are. So now, take this seriously and plug your lifespan into the math. If we give you a fantasy ride, a ship that can maintain a constant speed of 100,000 miles per hour, that's faster than any crew has ever flown. But still below Parker Solar Probe, and ignore all the messy bits like speeding up and slowing down. Just imagine you somehow get up to that speed and keep it non-stop for 50 years of your life. 50 years is about 438,000 hours. Multiply that by 100,000 miles per hour, and you get around 43.8 billion miles travelled in one long, continuous arc that sounds massive. And inside the solar system you could reach and tour the outer planets. You could sweep through the Kuiper belt. You could stack up a path length bigger than Voyager's current distance from the Sun. All in one lifetime. But now compare that 43.8 billion miles to 1 light year. Remember, 1 light year is about 5.88 trillion miles. So your entire 50-year cruise at 100,000 miles per hour, your whole adult life spent just flying, doesn't even reach 1% of a light year. You don't get close to a star, you don't get anywhere near Proxima Centauri, you are still in the Sun's local neighbourhood, just very far out in the dark. So even when you bend the rules in your favour, give yourself a speed we don't yet have for crew, and give yourself a half-century of near non-stop travel, the numbers smack you down. Your lifetime is tiny against interstellar distances. And that's before we talk about the fact that you can't actually live in a ship that just accelerates forever without cooking your body with constant thrust. At this point you might be thinking, okay, but what about relativity? What about that thing in science fiction where time slows down for the traveller? Doesn't that help you? Doesn't that stretch your subjective lifetime so you can cover more distance before you feel old? Relativistic time dilation is real. It's not a story trick, it's part of how the universe works. But it only becomes strong when you're moving at a large fraction of light speed, something like half of light speed or more. At those levels, your onboard clock really does tick slower compared to clocks back on Earth. You age less than the people you left behind. But at the speeds we've actually reached, even with Parker Solar Probe, time dilation is basically non-existent. At a few 100,000 miles per hour, your time and Earth time are almost identical. If you pushed up to 10% of light speed, the effect is still small. You get a tiny advantage. Not the kind of huge stretch that turns decades into centuries from your point of view. You don't get a magic shortcut, you just get old on a very long trip. So here's the bottom line of this whole section. Your 80-year human lifespan, with maybe a few decades of real travel time inside it, is completely mismatched with the size of interstellar space. The speed of light is so high, and the distances between stars are so huge that even extreme speeds we dream about still barely let you touch your local neighbourhood. And at the speeds we can actually fly today, you are locked inside one star system for life, and that leads to the next hard layer of this problem. Even before you worry about higher speeds, even before you talk about fusion drives or fancy engines, there's something else that starts to fail long before the math runs out: your own body. If the clock is already against you, what happens when your bones, your eyes and your brain start breaking down just from being in space at all? The equations might say you could fly for decades, your engines could keep pushing, your trajectory could be stable, but your bones, your eyes and your brain are all saying something very different. They're saying absolutely not. Your body is the first hard limit on how far you personally can go. Start with the most basic problem, microgravity. When you're in orbit, you're basically in free fall around Earth. You feel weightless. That might look fun. You float, you spin, you do flips. But your body is built to live under gravity. Your bones expect to carry weight. Your muscles expect to fight against it every time you stand up, walk, or climb stairs. On the International Space Station, astronauts spend months in this weightless environment, even though they work out every day. On treadmills, bikes, and resistance machines, they still lose bone density and muscle mass. Their skeleton literally thins out, their muscles shrink, and their heart gets used to not pumping against gravity. When they come back to Earth, they often need rehab just to walk comfortably again. Their balance is off, their legs feel weak, their cardiovascular system has to readapt, and remember, these are missions measured in months, 6 months, maybe a little more, not 10 years, not 20. So here's the first hard question. If a few months of microgravity already start breaking you down, what happens if you try to stay out there for a year or longer? We actually do have some data on that. There have been a few long-haul missions back on the Mir space station. Cosmonaut. Valery Polyakov stayed in space for 437 days straight. That's over 14 months. That record still stands for the longest single continuous spaceflight. More recently, NASA astronaut Frank Rubio spent 371 days on the ISS in one mission, and several astronauts and cosmonauts have racked up more than 1,000 total days in space when you add multiple flights together. The key point is, humans can survive a year or more in orbit, but it is medically expensive. You're doing constant exercise, constant monitoring, constant countermeasures, you're tracking bone loss, muscle loss, heart function, immune changes. You're doing scans and blood tests, and even with all of that, these missions stress the body heavily. And this is still low Earth orbit, a couple of 100 miles up, with fast emergency return options and regular resupply. Basically the easiest possible place in space you can live. So if a year in the best case location already pushes our systems hard, what happens when you leave that safe zone and go much farther out? That's where radiation shows up as the next wall. Earth has a magnetic field. It acts like an invisible shield that deflects many charged particles from the Sun, and from deep space, the ISS, at roughly 250 miles up, still sits inside a big chunk of that protection. Crews there get more radiation than you do on the ground, but the levels are still manageable with current shielding and mission durations. Once you go beyond Earth's main magnetic field out toward the Moon, Mars, or deep interplanetary space, you lose most of that shield. Now you're exposed to galactic cosmic rays, which are very high energy particles coming from all over the galaxy, and solar particle events, big bursts of radiation from flares and coronal mass ejections coming off the Sun. You can block some of this with thick walls, water tanks, or special materials, but you can't stop everything without building a ridiculous amount of shielding, which makes the ship heavier and harder to push. For multi-year trips, the risk picture changes. It's not just about short-term illness. Now you're talking about significantly increased chances of cancer later in life, higher risk of cardiovascular disease, and possible neurological effects, because those particles can damage not just your DNA, but also your blood vessels and potentially your brain. The longer you stay out there, the more the radiation budget eats into what is considered an acceptable risk for a human mission. And that's before you even get into all the other strange ways space rewires you, physically and mentally. In microgravity, fluids in your body shift upward because they're no longer being pulled down into your legs. More fluid moves into your head, around your eyes and brain. Long-duration astronauts have come back with swollen optic nerves, flattened eyeballs, and changes in vision. Some of them have needed glasses after flight, even if they didn't need them before. This isn't just a minor detail. If your vision degrades seriously on a long mission, that can affect your ability to work, to read displays, to do repairs, to pilot vehicles. People also report changes in smell and taste and very sensitive skin. Things that normally wouldn't bother you can feel irritating or even painful. Your sleep cycles get messed up because you see 16 sunrises and sunsets per day in low Earth orbit, or you live under artificial light with no natural day-night cycle at all that hits your hormones and mood. Psychologically, you're in a small volume, with the same people doing high-stakes work under constant monitoring for months. Crews on the ISS already report mood shifts, sleep disruption, stress, and the strain of confinement. And they can still see Earth out the window, they can talk with mission control in almost real time, they know there's a way home in hours if something goes very wrong. Now stretch that to decades with long communication delays, no quick exit, and the knowledge that you may never see Earth in person again. We simply don't have real data on what that does to a human mind. So, when you put all that together, microgravity weakening your body, radiation hitting your cells, weird fluid shifts hitting your eyes and brain, and the psychological pressure of long isolation, what does that actually say about the distance you can personally cover? Right now, the longest single missions we have proven survivable are roughly in the 1 year to 1.5 year range, and even those come with noticeable physical and mental costs if you add better shielding, smarter mission design, and artificial gravity systems like spinning sections of a ship to simulate weight. You could probably push safe mission lengths out to a few years, maybe enough for a round trip to Mars plus some surface time, maybe enough for a multi-year deep space expedition within the solar system. But when you start talking about an individual human doing 20, 30, 40 years of continuous deep space travel with no gravity, higher radiation, no quick support and limited medical facilities, that's something today's biomedicine cannot honestly promise. We don't have evidence that a body like yours can stay functional in those conditions for that long. The stress on bones, muscles, organs, and a brain is just too high. And that means even before you hit the engineering limits of rockets and fuel and energy, your biology is already shrinking your realistic range. In one personal lifetime, your body is likely to cap you at missions of a few years each, maybe several of them over a career, but not one endless cruise into the dark, which is why, when we talk about how far you can go, we have to be honest. Your maximum distance is not just a number on a map, it's a fight between what the engines can do and what your cells can survive. So if your body locks you into missions of a few years, and your lifespan caps how many of those missions you can stack, the next question is simple and rough. With the rockets we actually have, and the ones we can realistically build soon, how far can those years of survival take you? Can you ever get beyond the inner solar system on the kind of fire and chemistry we're using right now? Let's strip it all the way down, no warp drives, no antimatter, no magic engines, just what we actually fly today, fire and chemistry, if all you get is chemical rockets. The same basic technology that launched Sputnik, Apollo, the Shuttle and Dragon. How far can you personally go in one lifetime? Chemical rockets are good at one thing, giving you a huge punch of thrust in a short time so you can escape Earth's gravity, they burn fuel fast, they throw exhaust out the back at high speed, and then they give you that brutal acceleration you need to get off the ground. But after that, their mileage is terrible. To go much faster, you'd need a ridiculous amount of fuel, and every extra pound of fuel makes the rocket heavier, which then needs even more fuel. You hit a wall very quickly. In practice, chemical rockets top out at speeds in the range of tens of thousands of miles per hour for crewed missions. Apollo's Saturn V is the classic example. It sent astronauts on a trajectory to the moon at roughly 24 to 25,000 miles per hour relative to Earth. At that speed, you can cover the roughly 240,000 miles to the moon in about 3 days, which matches what we actually did. Crew leaves Earth, does some course corrections, and a few days later they're in lunar orbit. So with chemistry alone, you can absolutely reach the moon, you can land, you can come back, that part is solved. The real question is, how far beyond that can the same basic tech push you, without becoming absurd in size and cost? Take Mars, this is the next big real target. At their closest, Earth and Mars can be somewhere around 35 to 60 million miles apart, depending on where both planets are in their orbits. One record close approach was about 34.8 million miles. That's the best case line between the two. But missions don't go in a straight line. They follow energy-efficient paths that take advantage of orbital mechanics. With today's tech and realistic trajectories, a one-way trip to Mars takes roughly 6 to 9 months. You launch when the alignment is right, you cruise for more than half a year, then you break into orbit or head straight into the atmosphere for landing. That kind of timeline is absolutely inside the endurance envelope we've already tested. It's longer than a typical ISS mission, but not by a crazy factor. It's comparable to Valery Polyakov's 437 days on Mir, if you count the outbound and inbound legs plus some time at Mars. So in your lifetime, with chemical rockets plus good mission design, a Mars mission is not fantasy. It's hard, it's expensive, but it's doable. You could even imagine doing it twice if you're lucky, one mission in your 30s or 40s, another in your 50s, with years of training and recovery in between. Now stretch that out into a whole career. What does an inner solar system tour look like if you stick with chemistry and play your cards aggressively? You could start with multiple trips to low Earth orbit, station work, short missions that already gives you millions of miles of travel because you're circling the planet at high speed over and over. Then you move on to the moon, maybe you do orbital missions, maybe you walk on the surface, a few separate expeditions across a decade. At some point, you get assigned to a Mars mission, 6 to 9 months out, months on the surface, 6 to 9 months back. That one round trip alone stacks up tens of millions of miles relative to the Sun. And in a very ambitious scenario, you might add in a side mission to a near-Earth asteroid. Those are space rocks that come relatively close to Earth's orbit, reachable with carefully planned chemical trajectories and not insane travel times. Each leg takes months, not decades. Each mission is within the kind of durations and radiation doses we can at least think about managing with current or near-future tech. By the end of this kind of career, your total distance travelled could easily hit the hundreds of millions of miles, maybe more, but notice where you still are. You're inside maybe 1 to 2 astronomical units of the Sun. That's inside the orbits of Earth and Mars, maybe nudging a bit beyond toward the asteroid belt. You're still very much near your star in cosmic terms. So why not go bigger? Why not take a chemical rocket and just keep going out? To Jupiter, to Saturn, to the outer planets, in theory, nothing. In physics says no, Jupiter sits at about 484 million miles from the Sun on average. Saturn is even farther. A clever gravity assist chain plus chemical burns could, on paper, throw a crewed vehicle that far. The problem is everything else to send a crew to Jupiter on chemistry. You need a huge amount of fuel, your ship mass explodes, your launch stack turns into something far beyond what we routinely build. The mission time stretches into many years, not just 1 or 2, and then you hit Jupiter's radiation environment. That planet has intense radiation belts that make Earth's Van Allen belts look mild. Flying a crewed ship through that region safely, for any serious time, demands heavy shielding, which makes the ship even heavier, which demands even more fuel, and the loop gets worse. So while a crewed Jupiter mission with pure chemical rockets is not forbidden by the laws of physics, it sits way beyond what current programs are willing to risk or pay for. You're stacking multi-year flights, high radiation, no quick return options, and insane launch mass. It's technically possible, but practically, with our budgets and risk tolerance, it's off the table for now. Pull it back to what's actually reasonable and tally it up. Several missions to low Earth orbit, a few lunar trips, and one aggressive Mars expedition, maybe with a near-Earth asteroid in the mix, across an entire career. That's your high-end, pure chemistry life. If you add up all the path lengths of those flights relative to Earth and the Sun, you could personally rack up over 1 billion miles travelled. That is huge on a human scale, more than 4,000 times the distance to the Moon, but on the cosmic scale it's tiny. 1 billion miles is only about 0.0002 light years. That's 2/10,000ths of a single light year. The nearest star is more than 4 light years away, so even after a lifetime of flying fire-breathing rockets, you are still nowhere near leaving the Sun's neighbourhood. Your entire career fits inside a thin bubble around one star. And that's the key tension. Chemical rockets can absolutely give you a busy, high-mileage life in space, orbit, the Moon, Mars, maybe asteroids, maybe an outer planet flyby. If civilization gets very bold. But they also lock you in, no matter how brave or committed you are. Chemistry alone will never turn you into a true interstellar traveller. You will die in the same star system you were born in. So if pure fire and chemistry max out at a few billion miles and a tiny fraction of a light year, the next question is obvious. If you want to push your lifetime range beyond Mars and maybe the asteroid belt, what kind of engines do you need? What happens when you trade raw blast power for slow, efficient, high-tech push that never turns off. You want to go farther than Mars in one lifetime. You want to push past the chemistry-only wall, then you need better engines, not magic ones, not warp drives, but real systems that already exist on paper or in space, and they all have to obey the same physics, no shortcuts, just smarter use of energy. Start with ion drives because they already fly. Spacecraft like NASA's Dawn mission used ion propulsion. Instead of big blasts of fire, you get a very gentle push. The engine spits out charged atoms, ions, at very high speed. The thrust is tiny. So small you could literally hold the engine in your hand while it's firing and not be knocked over, but it never stops pushing. Hour after hour, day after day, year after year, Dawn carried just a few £100 of xenon gas as fuel. That's not a lot. And across its mission it changed its speed by more than 25,000 miles per hour. That's not a guess. That's flown hardware. That's a real mission. It orbited Vesta and Ceres in the asteroid belt using that slow, steady push. Ion drives are far more efficient than chemical rockets in terms of how much speed you get per pound of propellant. But there's a catch. Ion engines are useless for launch from Earth. The thrust is way too low to lift off the ground. You still need chemical rockets to get into orbit, where ion drives shine is in deep space. If you're willing to accelerate for years, you can slowly build up very high speeds, so your mission profile changes. Instead of a loud, violent burn and then a long coast, you get a quiet, constant shove that gradually turns you into a fast-moving object far from the sun. So here's the question. If slow but efficient engines can keep pushing for years, what happens if you combine that idea with something much more powerful at the start, something nuclear? Back in the 1960s and 70s, the United States actually built and fired nuclear thermal rocket engines on the ground under a program called NERVA. These weren't just sketches, they were real test articles. The idea is simple. Instead of burning chemical fuel and oxidizer in a chamber, you run liquid hydrogen through a nuclear reactor, heat it up to very high temperature, and shoot it out the nozzle. Because the exhaust is hotter and lighter, it moves faster, and that gives you better performance. In practical terms, nuclear thermal rockets promise roughly twice the efficiency of the best chemical rockets. In rocketry language, that means a much higher specific impulse. In normal language, it means for the same amount of propellant, you get more speed, or you can carry more payload to the same speed. No one has flown one in space yet. Not because the physics is shaky, but because of safety. People get nervous about putting nuclear reactors on top of rockets, especially if there's a chance of a launch failure scattering reactor parts over land or ocean. So nuclear thermal is sitting in this strange place. It's not science fiction. We already know how to make a working reactor engine, but turning it into a flight system means dealing with regulations, public opinion, and a lot of engineering to make sure it's safe in every failure mode. Then there's a more advanced idea, nuclear electric propulsion and other hybrid stacks. Here the nuclear reactor doesn't heat the propellant directly. Instead, it works like a power plant. It generates electricity. That electricity then drives electric thrusters, like ion engines or Hall effect thrusters, so you get the steady, efficient push of an ion drive, but with a lot more power behind it than solar panels can provide, especially far from the sun. These concepts aren't just in wild future papers, they show up in serious studies for Mars cargo ships and outer-planet missions. You use chemical rockets to launch the stack and maybe to escape Earth's gravity well, then a nuclear reactor and electric engines take over for the long cruise, slowly but steadily ramping up your speed. In your lifetime, it's very plausible that unmanned nuclear electric craft will be used regularly for deep space missions. And if safety hurdles get resolved, crewed nuclear stages could shorten Mars trips and make long missions into the asteroid belt more realistic. So what does that mean for your personal maximum distance if we step away from today's pure chemical rockets and assume advanced, but still plausible propulsion? Imagine you sign up for a deep space mission in the second half of your career. By then you've done the usual low Earth orbit, maybe the Moon, maybe even Mars. Now you climb on board a nuclear-augmented ship designed for a multi-year expedition. Instead of just going from Earth to Mars and back, this mission does more. You might depart from Earth or Mars orbit, spiral outward under electric thrust, pick up speed over months and years, head into the main asteroid belt, visit one or more large asteroids, and maybe, with enough shielding and careful planning, do a flyby in Jupiter's neighbourhood, not diving through the worst radiation zones, but getting close enough to sample that part of the solar system. During all that time, your engines are sipping propellant and adding speed. Your path relative to the sun could span several billion miles. On one mission like that, your personal distance travelled could jump from just Mars level, tens or hundreds of millions of miles, up into the multi-billion mile range. You would still be nowhere near another star. Not even close, but compared to a career limited to low Earth orbit and a single Mars trip, your reach inside the solar system would be dramatically larger. You would actually feel the scale of the outer regions, not just read about them. But now comes the part that always pulls everything back down. None of these systems are stopped by physics, they are stopped by mass and safety. Nuclear stages mean putting reactors on rockets, which triggers hard questions about what happens if something explodes during launch. Who is responsible? How much risk is acceptable? And how the global public reacts to a nuclear accident connected to a space mission that can delay or kill programs even if the engineering is solid. Ion propulsion and nuclear electric designs demand long, delicate missions, where a failure in the power system or in a key thruster months or years into the flight can cripple the whole thing. You need ultra-reliable reactors, ultra-reliable engines, and extensive redundancy, which adds complexity and mass. Every extra pound is something you have to accelerate, which shapes how fast you can go and what trajectories make sense towards. So your lifetime range is not just a function of what physics allows, it's a function of what your civilization is willing to build, pay for, launch, and risk. On paper, with nuclear thermal, nuclear electric, and ion drives, one human life could cover billions of miles more than pure chemical rockets alone. In practice, your actual path will be determined by committees, budgets, and public fear, as much as by rocket equations. And even if you solve the engine side, there's one more trick you can use that doesn't come from burning more fuel at all. You can steal speed from the planets themselves for free. Which leads to the next question. If pushing harder is expensive and risky, can you bend your path around massive worlds and let their gravity do some of the work? And how far could that boost carry you if you dedicated a huge chunk of your life to one giant slingshot-driven journey? You actually can cheat a little in space, not on the physics exam, but with the planets themselves. Instead of burning absurd amounts of fuel to speed up, you can use big worlds as moving anchors, swing past them, and walk away with more speed than you had going in without paying for all of it in propellant. Here's how that works in simple terms. Imagine you're falling toward Jupiter. It's huge, it has strong gravity. As you dive in, you speed up, then you swing around behind it and fly back out to someone sitting on Jupiter. Your speed in and your speed out relative to the planet are almost the same. But remember, Jupiter itself is orbiting the Sun at a very high speed. So when you compare your path before and after the flyby from the Sun's point of view, you've stolen a tiny bit of Jupiter's orbital energy. That tiny bit for the planet is massive for you. Suddenly your spacecraft is going tens of thousands of miles per hour faster or slower relative to the Sun, depending on how you flew the maneuver. That is a gravity assist, or gravity slingshot. This is how missions like Voyager and New Horizons reached such high speeds without carrying an impossible amount of fuel. They bent their paths around giant planets and let orbital mechanics do some of the work. So when you hear about a probe getting a Jupiter assist or Saturn assist, that is literally the mission trading path geometry for speed, changing direction and velocity by carefully timing how close and at what angle it passes the planet. No engines required during the swing, just precise navigation and trust in gravity. Voyager 1 is the classic case. Launched in 1977, it did a flyby of Jupiter, then a flyby of Saturn. Those two assists flung it onto a trajectory that is now carrying it out of the solar system. Its current speed is around 38,000 miles per hour relative to the Sun. That escape trajectory is not something a chemical rocket on its own could have given it without absurd fuel mass. The gravity assists were the key. Without those boosts, Voyager 1 would still be somewhere much closer in, and it would never have reached the heliopause region within the span of a human lifetime. So if uncrewed probes can ride these cosmic slingshots, the next question is obvious. Could you? Could a human actually sit inside a spacecraft that follows a similar route? Earth to Jupiter, to Saturn, to the deep outer solar system? In principle, yes, nothing about the gravity assist technique cares whether the payload is a camera or a person. A piloted craft could launch from Earth, do a deep space cruise, arrive at Jupiter, thread through the system to pick up speed and bend its path, then head to Saturn, repeat the trick, and ride that new trajectory out toward the Kuiper Belt and beyond. The same math applies, the same boosts are available. The difference is that now you have fragile bodies and minds on board. In practice, the radiation environment around Jupiter is one of the big blockers. Jupiter has extremely intense radiation belts, much stronger than Earth's. A ship flying close to the planet would take heavy radiation doses if it wasn't very well shielded. That means adding a lot of mass for protection, which then affects how you launch, how you power, and how you maneuver the vehicle, and it all extends the mission timeline. On top of that, the travel times are long. A deep outer planet tour using gravity assists and advanced propulsion is not a 2-year road trip. You're looking at mission durations on the order of a decade or more. By the time you launch, cruise out to Jupiter, do your flybys, reach Saturn, and then coast farther, a big fraction of your life has been spent in deep space far from any easy return path. So here's the trade-off you start to see. Yes, a human could, in theory, ride a Voyager-style route, but it turns your life into a long, high-risk arc, with no fast exit and no guarantee of getting back before old age catches up. Now push this idea to its limit, and ask, if you really committed, if you gave 10 to 15 years of your lifespan to one massive deep space expedition, combining gravity assists with advanced propulsion like nuclear, electric, or ion drives, what kind of distance could you personally cover on that single mission? You might start close to home, maybe you do shakedown flights in Earth and lunar space, then you board your flagship, it spirals out from Earth, maybe does a Mars flyby or stop, then plots a course to Jupiter, picks up speed there, swings to Saturn and then continues outward, maybe toward Uranus or Neptune, or into the Kuiper Belt region. At every major planet, you either steal or shed a bit of orbital energy, reshaping your path without burning all your fuel at once. By the time you're 10 or 15 years into this arc, your path length relative to the Sun could be in the tens of billions of miles, easily an order of magnitude beyond a simple Earth to Mars and back profile. You could have personally crossed regions of space that, until that point, only probes like Voyager or New Horizons had visited. You'd be one of the very few humans to see Jupiter, Saturn, and possibly beyond, up close and with your own eyes. But then you look back at the scale we talked about earlier. Tens of billions of miles still translate to only a few thousandths of a light year. The nearest star is more than 4 light years away. So even after spending a huge chunk of your adult life on one deep space mission, you're still solidly inside the Sun's domain. You haven't come remotely close to another star. Your journey is massive for a person, but tiny for the galaxy. That brings you to the hardest decision in this whole how far in one lifetime question. Every big trajectory you choose has a cost. The more you push for a crazy deep space path, using gravity assists and advanced engines to go as far as possible, the more of your finite lifespan you burn on one mission. If you sign up for a 10 or 15 year expedition, you probably are not also doing multiple Mars landings, multiple lunar tours, and a long career on stations. You're trading a broad set of shorter, closer experiences for one long, lonely arc outward. So your achievable distance is not just a technical limit, it's a personal choice. Do you spend your life on lots of shorter hops near Earth, stacking up missions in low Earth orbit, on the Moon, maybe Mars, keeping communication delays short and always having a way home within months? Or do you commit to one giant trajectory, one shot at the outer dark where you leave, swing past giant planets once, and never live long enough to repeat it? And even if you decide to push outward as far as engines and gravity assists will take you, there's another hard boundary sitting in front of you, because the solar system itself has an edge, a real physical transition zone where the sun's influence fades and interstellar space begins. So the next question is, could you in one lifetime ever ride a ship all the way out there to the true edge of the sun's bubble? Forget the edge of the galaxy for a second, that might as well be fantasy. Here's the harder, more honest question. Could you personally ever ride a ship all the way to the edge of the sun's influence? Not out of the galaxy, just out of the sun's bubble, to the real border between our system and everything else? To answer that, you need to know what that edge actually is. The sun doesn't just shine light, it blows a constant stream of charged particles outward in all directions. That stream is called the solar wind. Close to the sun, it dominates the space environment. It forms a kind of bubble around the solar system. Farther out, that wind gets weaker. And eventually the pressure from particles in interstellar space, the stuff that fills the galaxy, pushes back hard enough that the solar wind can't keep expanding. The place where the solar wind finally loses and interstellar plasma takes over is called the heliopause. It's not a hard shell, it's not a solid barrier, but it's a real boundary. Inside it, the sun's particles and magnetic field are in charge. Outside it, the environment is set by the galaxy. In 2012, Voyager 1 crossed that boundary. Its instruments measured a sharp change in particle types and directions. That's when we say it entered the local interstellar medium. From that point on, it was truly between the stars, even though it was still much closer to the sun than to any other star. So where is this place in actual numbers? Not just words. Voyager 1 has been moving away from the sun at around 3.6 astronomical units per year. 1 astronomical unit is the distance from Earth to the sun, about 93 million miles. Multiply that out. 3.6 astronomical units per year is roughly 335 million miles per year. Year after year, with no stops, Voyager crossed the heliopause at a distance of around 120 astronomical units from the sun. 120 times farther than Earth. That's what that means. Take 93 million miles, multiply by 120, and you get tens of billions of miles from the sun. And it's still going. That is the scale you're dealing with just to exit the sun's wind bubble. Forget reaching another star. This is just getting to the edge of the solar system's influence. So now the question hits you directly. Could a human ship ever match that path? Not a tiny probe, but a vehicle with people on board with air, water, food, shielding, and everything else you need to stay alive for decades. Technically, yes, the physics doesn't forbid it. You could design a long-duration spacecraft with very robust shielding, thick walls, maybe water or hydrogen-rich material to help block radiation. You could give it advanced propulsion, nuclear electric engines, ion drives, maybe even nuclear thermal stages. You could plan a route that picks up speed from gravity assists around planets and then spends decades cruising outward. If you wanted it to be fully self-sustaining for centuries, you'd probably end up with a multi-generation vehicle, where the people who arrive are not the people who launched, but from a pure, can the ship move like Voyager perspective, it's possible. The problem is not the math of the trajectory, it's the biology and psychology of the crew. A single human spending 40 or more years in deep space, outside Earth's magnetosphere, at huge distances from home, under constant radiation exposure, with no quick rescue, is completely untested. We have no data for that. We have data for 1-year missions, and combined totals of around 3 years spread across multiple flights. That's it. You'd be stacking unknowns on unknowns. You'd be betting that your body, your brain, and your life support systems can handle a time span that is basically your entire adult life with no realistic way to abort and go home early. So if follow Voyager all the way is technically possible but biologically and socially extreme, what is the more realistic upper limit for you, personally, in your lifetime? A grounded scenario is something called an interstellar precursor mission. Not actually going to another star, but going far enough out that you're sampling the environment on the way there. In this kind of mission, a crewed vehicle might use nuclear-augmented propulsion and gravity assist to first reach the outer planets, places like Jupiter, Saturn, maybe Uranus and Neptune. From there, it pushes even farther, aiming for the region where the sun's influence is weaker, maybe heading toward the inner parts of the Oort cloud, the distant shell of icy bodies that surrounds the solar system. In that model, you, as a crew member, might ride the ship out to somewhere between 50 and 100 astronomical units from the sun, that's 5 to 10 billion miles outward, still inside the heliosphere, maybe approaching its outer regions. At that point, the mission might release smaller robotic probes to continue on to the heliopause and beyond, while the main crewed vehicle either loops on a long return trajectory or accepts that this is a one-way, end-of-life voyage. From your perspective, that would mean you personally reach distances of 50 to 100 astronomical units from the sun, far beyond the orbit of Pluto into true deep space. Your view of the sun would be of a very bright star, not a huge disk. Your communication delays with Earth would be measured in hours, not minutes. Your total path length over the mission could easily reach tens of billions of miles. It would be the most distant any human has ever travelled. So is the heliopause itself, that 120 plus astronomical unit boundary, actually in reach for one human life if we're honest, with near future technology and very aggressive mission design, maybe, but only as one-way late life mission, where you accept that you will not come home. You launch on a vehicle that spends decades creeping outward. You manage your radiation exposure as best you can. You run your life support systems until they fail. And if everything works, you or your crewmates might live long enough to see the instruments tick over as you cross the heliopause, from inside the sun's bubble to true interstellar space. That's the key. What Voyager has proved is that the path is physically navigable. You can travel from Earth's orbit to the heliopause on a predictable track, with steady speeds and instruments that survive. Nothing magical blocked it. No invisible wall, just distance and time. The real question now is not, can a ship do it? It's, will any society ever agree to send people that far for that long without a way to bring them back? That's an ethical decision as much as an engineering one. And even if you do somehow push a human body, a human mind, and a human ship all the way to the heliopause, you're still nowhere near another star. You have done something historic and extreme, but the nearest true destination beyond the sun is still more than 4 light years away. So the next question is harsher than all of this. If it takes tens of billions of miles just to step outside the sun's bubble, what does the distance to the closest star actually mean for you? In one short human life, how bad is that number when you put it next to everything we've talked about so far? You hear that the nearest star is only 4.24 light years away, and it sounds almost friendly, like it's in the neighbourhood. But when you unpack that number in plain miles, it stops being friendly very fast. It turns into something that might as well be infinity for one human life. Start with the basic conversion. 1 light year is just the distance light travels in 1 year. Light moves at about 670 million miles per hour. Multiply that by all the hours in a year, and you get a distance of roughly 5.88 trillion miles. That's 1 light year. Now take Proxima Centauri. About 4.24 light years away, you're looking at something on the order of 25 trillion miles from Earth. That's the closest star beyond the sun. Not some distant galaxy, the closest. Your brain is not built to picture 25 trillion miles. You can imagine a few hundred, a few thousand, maybe a few million. If you think about airline travel or around the world distances, trillions are so far outside normal experience that the number is basically an abstract wall. And that's the core problem. When we say space is big, this is what it actually means. Now compare that to the hardware we already talked about. Take Voyager 1, our current distance champion. It's moving at around 38,000 miles per hour away from the sun. That speed is far beyond anything humans have flown on board. And it has been doing that for decades. If you ask how long it would take something moving that fast across 25 trillion miles and reach Proxima Centauri, the answer is ugly. You're talking roughly 73,000 years, give or take. That's longer than all of recorded human history. That's older than agriculture. older than cities, older than writing. If you tried to picture your family line over that timescale, you could stack your ancestors back to the Ice Age, generation after generation, and still not finish the trip. Voyager speed feels fast, but against star distances, it is crawling. It shows you in hard numbers that just pointed at Proxima and go is not a real plan, not for anyone whose lifetime you care about. Maybe you think, fine, Voyager is a slow robot. What if we send people at Apollo-type speeds? Those missions to the moon use departure speeds of around 24 to 25,000 miles per hour relative to Earth. That's enough to go 250,000 miles in about 3 days, which feels impressive, but now run that speed against the star distance. 25,000 miles per hour across 25 trillion miles gives you travel times in the range of hundreds of thousands of years. Not tens of thousands, hundreds of thousands. Your 80-year life, even stretched to the maximum, doesn't even register on that timescale. You could live and die, and your entire civilization could rise and fall many times without the ship ever getting close. So at real flown speeds, both robotic and crude, the nearest star is effectively unreachable for a single human lifetime. You're not arguing about whether you can go, you're arguing about whether your species can maintain a project across longer than human civilization has existed so far, which is a completely different level of difficulty. That's why people start asking the next question. What if we go way faster? What if we hit a serious fraction of light speed? Not 1%, not 2%, but 10%. Now you're talking about engineering dreams like fusion drives, antimatter engines, or huge laser-pushed light sails. These are not things we can build today, but they are at least based on known physics, not fantasy. 10% of light speed means moving at about 67 million miles per hour, not hundreds of thousands, tens of millions. At that speed, crossing 4.24 light years is a different game. If you could somehow jump to 10% of light speed and later slow down, the raw crossing time is a bit over 40 years one way. In onboard time, add in the fact that you need to accelerate up to that speed and brake at the other end, and you're still sitting in a window that is on the edge of one human lifetime. If you left in your 20s or 30s and everything worked, you could in principle arrive at Proxima's neighbourhood before you died. But notice what you had to assume. You need engines that can accelerate a crude ship to tens of millions of miles per hour. You need shielding strong enough to handle constant impacts from dust and radiation at that speed. You need a life support system that works reliably for decades with no resupply. And you need energy budgets that make today's rocket launchers look like toys. We are talking about power levels closer to what nations use, not what one launch pad uses. This is far beyond anything we have ever built or seriously funded, even as a prototype. So 10% of light speed sits in this awkward place. The physics says it's possible in principle. The travel time says it just barely fits inside a human lifespan. But the engineering, money, and risk push it way out toward the edge of what any real civilization is likely to attempt, especially for a small crew on a one-way or maybe one-shot mission. And here's the kicker. Even if you personally somehow rode such a miracle ship and hit that 10% of light speed mark, the galaxy still dwarfs you. The Milky Way is roughly 100,000 light years across. That's the diameter of the disk of stars we live in. If you travel at 10% of light speed for your entire active life, say a few decades of ship time, maybe you cross 20, 30, 40 light years, enough to visit a few nearby stars, a handful of systems in the local bubble. Take the upper end. Say you manage 40 light years in one incredible once-in-all-history mission. That's 40 out of 100,000. You've crossed about 0.0004 of the galaxy's diameter. A tiny slice. If the galaxy was shrunk down to the width of the United States, your entire lifetime journey would be like moving a couple of city blocks. That's it. A huge achievement compared to where we are now, but almost nothing compared to the full structure you're sitting in. So when you zoom out, stars really are monsters in terms of distance. Even the close ones are separated by gaps that turn our fastest probes into slow crawlers, and even the wildest near-future propulsion ideas only scratch the immediate neighbourhood. Your lifetime looks microscopic compared to those scales, and that's before you account for something else. Once you start moving at those extreme speeds, the clocks themselves stop behaving the way you're used to. Time for you and time for people back home no longer match. Which raises a different kind of question. If you can't beat the speed of light, could you at least bend the experience of time so your own clock stretches farther than everyone else's? To find out, you have to let relativity into the conversation and see whether it's a real travel hack for you, or just another way the universe reminds you how small your lifetime is. If you can't beat the speed of light, you might still think you can beat the calendar. Maybe you don't live longer, but your time could run slower than everyone else's. From your point of view, that's the promise people grab onto with relativity. You don't change the laws of physics, you just bend how time feels. The first thing you need to know is this. At the speeds we actually fly today, relativity is basically asleep on the International Space Station, or even on the record setting. Parker Solar Probe, your onboard clock and the clock on Earth tick almost identically. The difference is so tiny you need very precise instruments to even see it. In normal life, it doesn't matter. For your body, a year in orbit is basically a year on the ground, from a time dilation point of view. Real changes start when you push up to a serious fraction of light speed, roughly half of light speed or more. Above that range, a thing called Lorentz time dilation starts to kick in hard. All that means in plain language is this: the faster you go, the slower your time passes compared to someone staying still. You don't feel anything strange. Your heart rate feels normal, your watch looks normal. But if someone on Earth compares their clock to yours later, they see that less time passed for you. So here's the key threshold. Below those high fractions of light speed, relativity gives you almost nothing. Above them, it becomes a big deal. Suddenly your aging slows down relative to people back home. Your one lifetime can cover more distance than their calendar would normally allow, at least from your own point of view. Now take a more extreme case, just as a thought experiment. Imagine a starship that can cruise at 90% of light speed. That's 0.9 c. You're now way beyond 10% light speed fantasies. You're in a regime where relativity is loud. At this speed, the time dilation factor is a bit over 2, meaning that for every year that passes on your ship, more than 2 years pass on Earth. If you travel for, say, 20 years on your onboard clock, roughly 40 plus years could pass back home, maybe a little more depending on how you handle acceleration and braking. At that kind of cruise, you could, in principle, cross tens of light years in your own lifetime. If you push the speed even closer to light speed, the effect gets stronger. You could stack up a path of dozens or even hundreds of light years in your proper time, while entire centuries, maybe longer, tick by on Earth. From your seat on the ship, the trip is long but not insane. From Earth's point of view, you left, history rolled forward, and by the time you arrive, your starting world is part of the past. This sounds like a cheat code, right? You don't live longer, but you can jump far ahead in everyone else's timeline. The catch is the price tag. And it's brutal. The problem is energy. The faster you go, the more energy you need to get there. And as you approach light speed, that energy requirement doesn't just rise in a straight line, it climbs sharply, pushing a small object to 90% of light speed. Already takes a huge amount of energy. Pushing a crewed ship with people, supplies, shielding and structure takes an absurd amount. You're talking about energy on the scale of what entire countries generate, poured into one vehicle not for a second, but sustained over long acceleration phases, and then you have to do it again in reverse to slow down at the destination. You can't slam into a new star system at 90% of light speed and hope for the best. That is not pessimism, that's just the math of kinetic energy at those velocities. It is deadly if you cannot control it precisely. So even though relativity gives you this nice feature where your time runs slower at high speeds, it only turns into a real travel hack if you can pay the insane energy bill and build systems that can safely handle that much power without killing the crew. That's the real wall, not the equations themselves. Once you accept that, the question how far can you go in one lifetime splits into two different answers, and they do not match. On the ship, your proper time is all that matters to you. If your engines and shielding are good enough, you could, in theory, cross tens or even hundreds of light years before your body gives out. Your onboard clock might say 50 years. You leave, you age, you work, you arrive, and you die of old age on the far side of some distant star neighborhood. But on Earth, the story is completely different. Their clock is not slowed in the same way. By the time you arrive, many more years have passed for them. Depending on your speed, it could be centuries. In some extreme cases, it could be longer. Entire civilizations might have risen and fallen. Tech levels might have changed beyond recognition. The people who launched you, the language you spoke, could all be gone. Your one lifetime becomes a bridge between two very different versions of the universe. So in a relativistic starship, your range in one lifetime is really two different numbers. Ship time distance, which can be huge if you push speeds high enough, and Earth time distance, which looks even larger, but at the cost of you being totally out of sync with the world you left. You don't get both. You either stay aligned with Earth and go slow, or you go fast, use time dilation, and say goodbye to any expectation of returning to the same civilization you departed. Now here's the reality check that matters most right now, and for the near future. No project we have is remotely close to building a ship like this. We test relativity all the time in particle accelerators, where tiny particles move at more than 99% of light speed. We correct for relativity in GPS satellites, because their clocks run just a little differently than clocks on Earth. The equations are real, the effects are measured. This is not speculation. But scaling that same physics up to a massive, shielded, life-supporting starship is an entirely different problem. Nothing in current engineering, budget planning, or space agency roadmaps points to a relativistic crewed ship in your lifetime. Maybe not even in your great-grandchildren's lifetime. So for now, relativity is more of a limit. You're a spect and a tool you use in navigation math than a travel trick you can actually exploit as a person. And even if one day a relativistic starship becomes real, time dilation doesn't solve every problem. It doesn't grow food for you, it doesn't recycle your air and water. It doesn't fix radiation damage or repair aging machinery. You can bend how time passes, but you still need an artificial mini-planet around you to survive the journey. Which raises the next harsh question. If you want to stretch your range to the absolute max, can you actually carry what amounts to an 80-year world on your back and keep it running in the middle of nowhere? You're not just moving a person through space. You're trying to move an ecosystem, a tiny artificial version of Earth that has to keep you breathing, hydrated, fed, and mentally stable, not for a week or a year, but potentially for decades. And right now, we're barely at version 1 of that idea. Look at what we actually have, the International Space Station. It's been hosting humans continuously since 2000, orbiting only about 250 miles above Earth. That's a short flight distance. But in terms of life support, it's a big deal. The ISS recycles water, cleans air, grows a little bit of food in experiments, and it tests technologies for closed systems. But here's the key point. It is not self-sufficient at all. Cargo ships bring up food, spare parts, oxygen tanks, clothes, tools, scientific gear. They also take away trash, broken hardware, and waste. The station's systems wear out and need replacement. Filters clog, pumps fail, valves leak. The ISS is a laboratory platform, not a sealed world. If you cut off resupply from Earth, the countdown would start, and eventually something critical would break that the crew couldn't fix with what they had on board. So the obvious question is, if our best space habitat still needs regular delivery trucks from the ground, what happens when you take Earth out of the loop completely and expect your ship to run on its own for 10, 20, or 40 years? We've tried to test that idea here on the ground in controlled experiments like Biosphere 2. That was a sealed complex in Arizona where people tried to live inside a closed ecosystem with their own plants, soil, air, and water cycles. The goal was to see if a small Earth-like system could stay in balance without outside input. In reality, things went wrong fast. Oxygen levels dropped, carbon dioxide rose, some species exploded in number, others collapsed. The ecosystem drifted away from what humans needed. That was with gravity, with normal access to spare parts, with outside help available if things went bad, and even then, keeping the system stable was incredibly hard. Now imagine doing that not for a couple of years, but for decades inside a starship with zero resupply if Biosphere 2 is level 1, then a fully closed starship life support system is like doing that experiment multiplied by 10,000, with people's entire lives on the line and no door you can just open if something tips out of balance. So you have to ask, if you actually tried to build this for a real mission, what do the numbers look like? How much food, air, water, machinery, and backup gear does a small crew need to survive for that long? Even with good recycling, you never get to 100%. Right now, advanced systems might reach something like 90 to 95% recovery for water and a big chunk of the air. That means you still lose a few percent over time to leaks, inefficiencies, and contamination. To cover that, you need stores or backup chemistry to remake what you lose, and all of that takes mass, machinery, and energies. Food is even tougher. If you don't want to carry decades of pre-packaged meals, you need to grow it. That means big growing areas, lighting or sunlight collection, nutrient solutions, temperature control, pest management, and people or robots to tend it. Current tech suggests you'd need a lot of space and a lot of power to feed even a small crew for decades. And that's before you count the energy for your engines and other systems. Every extra pound of equipment, every greenhouse panel, every water tank and filter is something your propulsion system has to push. The heavier your ship, the harder it is to reach high speed, the more fuel or power you need, and the more you cut into the maximum distance you can cover before your resources run thin. So now you have a sharp split between two types of missions, short hops and lifetime arcs. A week-long lunar mission is straightforward. You pack consumables, bring everything you need, and accept you're not staying long. Even a year on Mars with resupply from cargo ships is hard, but you can at least imagine it. You stockpile food, fuel, spare parts, and slowly build infrastructure on the surface. But a 40-year starship or heliopause arc is a completely different category. That's not a ship in the way we normally use the word. That's a flying city, with industrial-level life support, power generation, manufacturing, farming, medical systems, and recycling. It has to repair its own parts, remake broken components, maybe even smelt metals or fabricate electronics, all without outside help. Building something like that in your lifetime is not a normal space program. It's a mega project on the scale of global civilization. You'd need massive funding, global cooperation, and decades of development before the first crew ever boards. And all of that loops back to the simple question we started with. What does this do to how far you can personally go in one life? Biology plus logistics crush your theoretical range down to something much smaller than the propulsion math alone would suggest. Even if rocket physics would allow you to accelerate to crazy speeds, even if trajectories to the heliopause or beyond look clean on paper, if you cannot guarantee that your crew will still have working air scrubbers, safe water, steady food, stable psychology, and repairable hardware, 20 or 30 years into the mission, then your functional range shrinks to whatever you can support reliably. In practice, that probably means missions that last a few years and stay within a few years of travel time from Earth. So your real lifetime distance is not set just by how powerful your engines are. It's set by how long you can keep a tiny, fragile ecosystem alive in a hostile environment, and how far you're willing to ride inside that system knowing there is no easy exit. And even if you solve that, there's another invisible limit waiting outside Earth's magnetic bubble. Because between the stars, space isn't empty. It's full of high-energy particles that slowly damage everything, including you. The space between the stars is not empty. It's a slow, invisible storm. If you step outside Earth's protection for long enough, that storm doesn't just hit your ship, it hits you, particle by particle, year after year. Right now, almost everything we really know about humans in space comes from low Earth orbit. That's where the ISS lives. A couple 100 miles up, even there you are still sitting under Earth's magnetic umbrella. Our planet's magnetic field reaches far out into space, shaping something called the magnetosphere. That field traps and deflects a lot of charged particles coming from the sun and from deep space. At 250 miles up, astronauts are above the thick atmosphere. But still inside most of this magnetic protection, radiation levels are higher than on the ground. They get more exposure from things like trapped particles in the Van Allen belts and occasional solar activity, but with current shielding and mission lengths of a few months to a year, the doses are elevated yet manageable. Agencies track every astronaut's lifetime dose carefully, but low Earth orbit is still the easiest radiation environment you can live in off Earth. Once you push beyond that shield for years, the game changes. Deep space radiation is not the same as low orbit radiation. Out between planets, you're constantly hit by two main sources: galactic cosmic rays and solar particle events. Galactic cosmic rays are high-energy particles, often protons and heavier nuclei, accelerated by violent events across the galaxy. Supernova, active regions around distant stars. They travel near light speed and can punch straight through normal spacecraft walls. Solar particle events are bursts of energetic protons and other particles launched during solar flares or coronal mass ejections. Those can spike radiation levels dramatically over hours or days. If you sit out there for a multi-year mission, especially unshielded, models say you could push astronauts to or past career radiation limits. You're raising long-term cancer risk, increasing chances of cardiovascular disease, and possibly impacting the nervous system. And unlike a single medical scan on Earth, this isn't a one-time thing, it's a constant background. Plus occasional dangerous spikes day after day for years. We're not guessing about this environment entirely. Robotic probes have been measuring it for decades. Spacecraft carry particle detectors and radiation monitors that count how many particles hit and at what energies. As you move away from Earth, those readings change. As you cross boundaries like the magnetosphere's edge, or farther out, the heliopause, the mix and intensity of particles shifts. Voyager is a clear example. As it approached and then crossed the heliopause, its instruments saw distinct changes in particle populations. Inside the heliosphere, you have more solar-charged particles and a certain level of galactic cosmic rays. Outside, the sun's influence drops, and the galactic component rises in a different pattern. That's how we know the boundary isn't just a theory. The environment genuinely changes as you move from inside the sun's bubble to the local interstellar medium. And for a human, that means the radiation story gets even harsher the farther you go. So if you start talking about decades-long trips, lifetime-scale voyages, what would you actually need to keep a crew safe enough to make the mission worth doing? You would not get away with thin aluminum walls and good vibes, you'd need real protection. For a start, you'd want massive shielding, materials that are good at stopping or slowing, charged particles, water is useful, hydrogen-rich plastics are useful. Some concepts even look at active magnetic or electric shields to deflect particles the way Earth's magnetosphere does. But physical shielding is still the core. For solar storms, you'd probably build a storm shelter in the middle of the ship, a small, heavily shielded compartment where the crew can hide during high-intensity events, surrounded by water tanks, supplies, and other dense material. Even with all of that, you're not getting exposure down to zero, you're just cutting the worst of it. The rest of the constant galactic background still trickles through. So you also have to accept that a decades-long mission means higher long-term cancer risk and other health hits. You can lower it, but you can't make it go away entirely. You're trading health margin for distance travelled, and every ton of shielding you add is a ton you have to accelerate. If you decide to pack your ship with thick walls, big water reserves and dense materials, your mass shoots up fast. More mass means more propellant or more power is needed to reach a given speed. If your propulsion is limited, that extra mass directly lowers the maximum speed you can realistically reach, which shrinks how far you can get within your finite lifetime. So radiation doesn't just threaten your health, it feeds back into your range. It literally drags down your achievable distance. This is why radiation acts like a hard distance cap for human missions. Even if you had a propulsion system that was almost magical, something that could push you to high fractions of light speed, the environment between stars would still hammer you with high-energy particles. If you can't shield the crew without making the ship impossibly heavy, or keep them alive under that exposure for decades, then there is a practical limit on how far a human can go before the health cost is simply too high. Long before you hit the theoretical physical limit, you hit a biological and ethical one. That's one of the reasons many serious interstellar mission concepts quietly push humans out of the main picture, or at least out of the awake, walking around looking out the window picture. Planners talk about uncrewed probes because robots don't get cancer and don't care about time, or they talk about frozen or hibernating crews, where people are in some kind of stasis for most of the journey, taking much lower effective doses and needing fewer resources until they arrive. Both approaches dodge the worst of the radiation and life support problem by not having fragile active humans sitting there for the entire ride. But even if you solve propulsion, shielding and life support on paper, even if you accept higher health risks for the sake of distance, there is another limiter that doesn't show up on a radiation map or in an engine diagram, because at some point, you're not just fighting physics, you're fighting your own mind, and the question becomes, can a human brain actually handle being locked in a metal box, far from Earth, with huge communication delays and no way out, for the kind of timescales we're talking about? You can armour a ship against radiation and micrometeorites. You can stack water tanks and metal walls around the crew. But what do you put between a human brain and years of isolation? You can't plate your thoughts in aluminum, and if your mind cracks halfway out to nowhere, the mission is done, no matter how good the engines are. Look at what we already see on missions we consider routine. Long ISS stays, astronauts who spend 6 months, sometimes close to a year in orbit, come back with more than just weak legs. They report mood swings, trouble sleeping, and a constant psychological workload. Early in the flight, you're adapting to weightlessness, new routines, constant noise, being watched by ground control. Later in the flight, you're dealing with monotony, distance from family, and the pressure of knowing that one mistake can break something important. And remember what the ISS has going for it. They have live video calls, near real-time conversations with loved ones, constant communication with mission control. They can look out the window and see Earth below, continents, storms, city lights. They know that if something goes very wrong, there is at least a theoretical way to get them home in hours, or days at worst. They're not in deep space. They're in what is basically high-altitude Earth neighbourhood. Now look at what we learn from analogues on the ground, places that try to mimic parts of that environment. Antarctic winter cruise, for example, live isolated in darkness and cold for many months. Submarine crews stay underwater in tight quarters. Mars analog experiments lock people in simulated habitats in deserts or remote locations. In all of these cases, humans can function. They can do their job so that they can cooperate, but interpersonal conflict, stress and depression are common. Small arguments get amplified, group dynamics become fragile, people burn out. And notice, all of those setups still have exits. If something truly goes wrong, if a person has a breakdown, if the situation gets dangerous enough, you can evacuate, or at least you know that land and normal civilization aren't light years away. None of these tests last decades. None of them are truly one way. No return sealed metal box for the rest of your life scenarios. They are hints, not proofs, that we can handle the psychological weight of a real starship. Then there's communication delay, which quietly turns into a psychological wall. In low Earth orbit, the delay is basically zero. You talk, they answer. On the way to the moon, it's just over a second, still fine. To Mars, when the alignment is bad, radio signals can take 20 minutes or more one way. That means a 40-minute round trip just to ask a question and get an answer. Real-time conversation is gone. You leave a message. They respond later. It becomes email with a lag, not a phone call. Push out to the outer planets and the delay stretches into hours. At Saturn, depending on positions, you're looking at over an hour one way. That means if you send hi, you might get hi back 3 hours later. That might be technically communication, but it's not socially alive. Go to Proxima Centauri. Now you're talking about more than 4 years one way. You send a message. The person who hears it is 4 years older by the time it arrives. They respond, 4 more years go by before you hear it. At that point, home stops being a place you interact with and becomes a history feed. A stream of delayed events, news and recordings from a world you used to live in. You can't call your family. You can't argue, joke or comfort in real time. By the time you hear that someone was sick, they have either recovered or died years ago. That kind of delay is not just a technical inconvenience, it's a psychological punch. It turns you into a ghost long before you actually die. Now layer relativistic travel on top of that. Imagine you sign up for a 30-year voyage on a ship moving at a large fraction of light speed. From your perspective, maybe 30 years pass on board. But because of time dilation, 40, 50, or more years pass on Earth. Everyone you know ages faster than you. People who were your age when you left are now elderly or dead by the time you come back. If you ever come back, their kids and grandkids are older than you look. The world you return to has decades of culture and technology you weren't there for. And that's the mild version. Push the speed higher and the gap grows. You might leave a 21st century Earth and come back to something that feels like another civilization. Or you might never return at all, you just live out your life on board, knowing that every year you experience is 2 or 3 years for the people you left behind. The psychological load of that level of disconnection, that irreversible split from your original world, is something we have never studied in any serious long-term experimental way. We have no data for it, just guesses. So even if you solve the radiation, even if you get the engines, and even if you somehow build a closed ecosystem that can run for decades, there's still this soft human limit sitting under all of it. The brain you are carrying is not a machine. It cracks under stress, isolation, guilt, boredom, grief, and the knowledge that there is no exit door anywhere, just vacuum in every direction. That's why in practice your lifetime travel distance probably ends up constrained by psychology as much as by fuel and shielding. Missions inside our solar system can still maintain meaningful contact with Earth. Even with minutes or hours of delay, you can still get new messages, new video, new instructions. You can still feel like you are part of a living world, not just a drifting relic. Once you push out into journeys where real-time interaction is gone and the delay stretches into years, you're asking the human mind to carry a weight we don't know that can handle. So the realistic cap for how far in one lifetime is likely not how far the engines can throw you, it's how far you can go and still be a human being in a human context. And that almost certainly keeps you inside one star system, probably inside the range where messages and support can still reach you within hours, days, or weeks, not decades. All of that sets the stage for the final step. If you accept these limits, lifespan, biology, hardware, and psychology, what does the absolute extreme lifetime mission look like? If you squeeze everything, tech, health, and risk to the edge, how far could one person born now realistically travel by the time they die? And what does that path from low Earth orbit to the deep dark actually look like when you lay it out end to end? Let's actually build your max range life, not with magic, but with aggressive, barely plausible tech. If everything breaks your way, what is the farthest storyline you could realistically live through before biology and time shut you down? You start in your 20s, Phase 1, low Earth orbit and the Moon, age 20 to 35. Your first years look a lot like what's becoming normal. You fly to low Earth orbit on vehicles, you spend months on a station, maybe the ISS, maybe a newer private platform. You do several missions, you rack up orbits, each lap is about 25,000 miles around Earth. You circle the planet again and again, thousands of times over a career. Then you graduate to the Moon, you join a lunar orbital mission, maybe you pass through a gateway station near the Moon, maybe you later land on the surface and spend weeks at a base there, working in low gravity, dealing with dust, running experiments. By the time you're 35, you've personally logged millions of miles in total travel, just from all those orbits, transfers, and lunar legs. But here's the catch. You are still under 1 light second from home. Light takes about 1 second to go from Earth to the Moon. You're close enough that real-time conversation still works. You're still in the tight inner bubble of the Earth-Moon system. Then comes Phase 2, Mars Explorer, age 35 to 50. Now your experience and health put you at the front of the line for the first serious deep space missions. You join a Mars architecture that uses either very efficient chemical propulsion or maybe nuclear-augmented stages to cut travel time and save mass. The basic profile is clear. 6 to 9 months outbound. Roughly a year on or near the surface, 6 to 9 months back. Each leg is tens of millions of miles, depending on the specific trajectory and where the planets are in their orbits. The whole mission easily hits hundreds of millions of miles relative to the Sun. You feel the isolation more now, communication delays in the minutes range, no quick return, radiation levels higher than low Earth orbit. You come home older, carrying physical wear and psychological scars, but also with the kind of experience only a handful of humans have ever had. If your body and mind hold up, you might do something like this once more. Later in that same phase, 2. Mars expeditions in one life is extreme but not impossible in this aggressive scenario. Then you hit phase 3, deep space trailblazer, age 50 to 65. This is where you stop playing it safe. Now you volunteer for a flagship mission. Something that isn't just about Mars anymore. This is a multi-year outer solar system expedition using nuclear electric propulsion, gravity assists and a lot of patience. You likely launch from cislunar space or from Mars orbit, somewhere already out of Earth's deepest gravity well. Your ship is bigger, heavier, more shielded, more like a small moving habitat than a capsule. The plan is ambitious. You depart the inner system, maybe swing by Mars again, grab a gravity assist from Jupiter to pick up speed and bend your trajectory, fly through the Jovian system, see its moons and its radiation belts from distance your bones can tolerate, then head onward, a Saturn flyby, maybe even a complex tour through its rings and moons, depending on how long your propulsion can keep nudging you. After that, you either commit to a slow looping return path, or accept that you'll end your life in deep space, with the Sun a bright star and Earth a memory you can't get back to in time. If you survive and your ship holds together, that one mission alone could add tens of billions of miles to your personal path. You'd be moving at speeds and along trajectories that today only probes like Voyager or New Horizons take, except now there are humans on board, looking out at environments we've only seen through cameras. Now, add all of this up over your entire life. Training flights, test flights, and low Earth orbit missions maybe give you 10 million or more miles by themselves. Lunar missions stack millions more. Mars flights jump that into the hundreds of millions, especially if you do more than one. And the deep space flagship, the big arc through the outer system, could easily push your total travel distance into the range of 20 to 30 billion miles, maybe more, depending on how aggressively the mission is designed and how long you live on board. That means your personal lifetime trajectory, your own line in space relative to the Sun, could rival or even exceed Voyager's current distance, not as a straight shot outward, but as a complex path, looping through different regions of the solar system, touching moons, planets, and deep space arcs on a human scale that is insanely big. You've gone farther than any human in history by a huge margin. But then zoom out. 20 to 30 billion miles is still only about 0.003 to 0.005 light years of total path length. The nearest star is over 4 light years away. The galaxy is about 100,000 light years across. So on a cosmic map, your entire story, all the launches, all the missions, all the risk and pain and distance fits inside a tiny circle around one average star. You never leave the solar system, not really. You never set foot in another star's domain. You die in the same gravitational well you were born in. And that's the harsh top line for maximum distance with non-magic tech. Even when you push your life to the edge, bend every engineering rule you can, and accept huge risks, your range stays local. You're a long-distance traveller locked inside one city, which raises the final uncomfortable question: what if in your lifetime we somehow do crack the tech to go truly fast, to hit serious fractions of light speed? Does that actually break this cage for you? Or does it just turn your life into a one-way ticket out of history? Now let's push optimism to the absolute edge. Suppose that before you die, humanity actually masters near light speed ships, not on paper, not just in sci-fi, but real hardware that can push a crew to a serious fraction of light speed. What does that do to your personal range, and what does it cost you? First, The tech leap today, we're talking about chemical rockets, ion drives, maybe nuclear stages to get anywhere near relativistic speeds. You need a completely different class of engine. People look at two big ideas, fusion starships and laser sail starships. Fusion would mean building a reactor that not only produces energy, but throws fusion exhaust out the back at enormous speeds, using the reaction products themselves as propellant. Laser sails, like the breakthrough Starshot concept, use huge ground or orbital lasers to push extremely light spacecraft with pressure from light itself. Breakthrough Starshot seriously studies sending tiny probes, just grams of electronics attached to thin sails, toward Alpha Centauri at about 20% of light speed. They'd get there in a couple of decades. That's not fantasy, that's real research. But here's the catch. Scaling from gram-sized probes to a crewed vehicle multiplies the difficulty massively. The basic physics is the same. You still need very high exhaust velocity or huge laser power, but now you also need full life support, shielding, redundancy, everything, and all of that. Mass multiplies the energy requirement to insane levels. Still, let's say somehow it happens, we solve fusion or build mega laser arrays, and we have a ship that can cruise at about 20% of light speed, 1/5 of the speed of light. What does a lifetime look like on that kind of machine? At that speed, you can cross 20 light years in about 100 years of ship time. If you leave Earth in your 30s, you won't live through a 100-year trip, but you don't need to go that far to reach something interesting. Targets exist within 10 to 20 light years. So if your ship accelerates up to that 20% light speed, cruises, and maybe uses clever braking methods at the far end, you could, in principle, reach a star system 10 to 20 light years away before you die on board. Your mission is clearly one way. No turnaround, no coming home. Your life ends out there, somewhere around a different star. This assumes the ship can protect you from radiation at those speeds, where every dust grain hits like a tiny bullet, and that it can keep life support running for decades without resupply. That's a huge assumption, but if we grant it, you finally see a path where a single human can actually move from one star system to another in one lifetime. The first true interstellar immigrant time dilation shows up here, but it doesn't dominate. At 20% of light speed, relativity gives you only a modest bonus. Your time runs a little slower than people on Earth, but not by a huge factor. Your subjective lifetime and Earth's calendar still line up fairly closely. You don't get the wild effect where you experience a few years and centuries pass back home. You might shave off a few years difference, but the main benefit is not the time warp. It's simply the raw speed being high enough that 10 to 20 light years becomes a career-length journey instead of a multi-generation project. The result is a reachable sphere around the Sun, roughly 10 to 20 light years in radius. Inside that bubble, in the real universe, there are dozens of stars, red dwarfs, sun-like stars, white dwarfs, and many known exoplanets. Some of those planets sit in what we call habitable zones, where temperatures could allow liquid water. In the wildest optimistic version of your future, if civilization climbs this tech mountain fast enough, a human born today could, in theory, die orbiting or even standing on a planet around another star within a few tens of light years of Earth. That is the extreme optimistic answer to how far in one lifetime, not tens of billions of miles, not the edge of the heliosphere, but another star, another sky, different constellations, a completely different neighborhood, reachable before your body gives out. If everything works and you accept that it is a one-way ticket, but you can't ignore why this might never actually happen. The energy cost alone is enormous. You need power on the scale of nations, directed into one project for years. Then you need engineering that can handle that power without killing the crew. You need a society willing to build a vehicle that will never pay off in normal economic terms, whose crew will never come home, whose success or failure will be known decades after launch. You're asking corporations to prioritize a multi-decade one-way star voyage for a tiny number of people over cheaper, safer options. Because remember, for exploration you don't need to send humans to get data. You can send robotic probes. They don't care about radiation, boredom, or time. You can flood nearby stars with small automated explorers long before you can realistically loft a single human at 20% of light speed. And as virtual reality and remote sensing get better, the pressure to risk real human lives on a mission that can never be rescued may stay low. It might simply never be the thing we choose to do. So even in the most generous optimism-maxed version of your future, relativistic travel for humans is not guaranteed. It's a high-risk, high-cost option that we may simply refuse to take. And that brings you to the final step in this whole story. Strip away the fantasies, keep everything you've seen, lifespans, biology, rockets, shielding, psychology, and maybe even extreme tech, and ask the only question that matters. In one human life, how far can you really go? And what does that answer say about your place in a universe this big? After all the math, the biology limits, and the rocket hardware, here's the uncomfortable answer to how far can you really go in one lifetime? Not very far in cosmic terms. Even in the best case, your range is small, and that's not an opinion. It's just what the numbers and your body allow. Start with the conservative near-term reality. No fantasy drives, just technology we already have or can clearly build. Chemical rockets as the core, maybe some nuclear augmentation for stages, better life support and stronger radiation shielding. In that world, what does your travel catalogue actually look like? You could go into low Earth orbit many times, stations, commercial platforms, short missions, long missions, training flights. That's a repeatable thing. We already do it. That alone stacks up millions of miles over a career, because every orbit is about 25,000 miles, and you do thousands of them. You could go to the moon and back several times, either in orbit or with surface stays at a lunar base. That adds a few 100,000 miles per trip. Round-trip Earth to moon and back is roughly 500,000 miles. With a serious push, you could join 1 or 2 Mars missions 6 to 9 months each way, roughly a year at or near the surface, total distances in the tens of millions of miles per leg, hundreds of millions for the full round trip. Combine that with your earlier flights and you're now very deep into the hundreds of millions, maybe nudging into the billions of miles of total path length. If the timing is perfect and the program is bold, you might also ride one extreme flagship mission out toward the outer planets, maybe a Jupiter or Saturn flyby with heavy shields and nuclear electric propulsion. That single trip could add billions of miles more. Add all of this together, and your lifetime distance, under conservative but ambitious assumptions, climbs into the tens of billions of miles. That is huge on a human scale, but still entirely inside the solar system. Your maximum reach, even after a life of non-stop spaceflight, never gets you beyond the sun's grip. You die orbiting the same star you were born under. Now shift to an aggressive but still plausible future. Here you assume we actually build serious nuclear electric stages, we field advanced radiation shielding, and we get partially closed life support systems that can run for many years with only limited resupply. Not perfect, but much better than today. What does that change for you personally? In that world, your lifetime could include multi-year tours in the outer solar system, not just quick flybys. You could spend years moving through the Jupiter and Saturn systems, maybe even visit Uranus and Neptune, using gravity assists and continuous low thrust to shape your trajectory. You'd live in deep space for long stretches, seeing worlds we've only seen with probes. On top of that, you might sign up for a one-way interstellar precursor mission. Something aimed not at another star, but at the boundary of the sun's influence, the heliopause, or at least the inner Oort cloud region. You'd ride a heavily shielded ship outward for the last decade or two of your life, knowing you will not return. Your personal endpoint might be 50 to 100 astronomical units from the sun, 5 to 10 billion miles out, or more in path length, depending on how your trajectory is designed. You would die as one of the most physically distant humans in history. Literally, one of the farthest pieces of biology your species has ever thrown into space, but you'd still be nowhere near another star, just very far out in the dark around this one. Now take the wild optimism mode, the extreme ceiling, assume civilization, in your lifetime, actually cracks high fraction of light speed propulsion, and commits to a generational flagship project, not a probe, but a crewed mission that uses fusion or laser sail style tech to reach a serious chunk of light speed, say 20% or more, and then uses that speed for a one-way journey. In that case, the absolute upper bound for one human lifetime changes. You're no longer talking billions of miles, you're talking tens of light years in your own proper time. Given a ship that can sustain you for several decades and protect you from high-speed radiation and impacts, you could, in principle, visit a handful of nearby star systems before you die on board. Maybe 10 to 20 light years away. Maybe more if you push your health and the tech to the edge. But to get that, you need a chain of technological and economic leaps that we have zero guarantee of making. You need power scales we've never controlled, reactors or laser arrays we've never built, and a society willing to launch a one-way multi-decade mission for a tiny crew that will never be rescued. If any part of that chain breaks, that upper bound collapses back down to the solar system. Now here's the cosmic punchline. Even in this extreme optimistic scenario where everything goes right, you will never cross more than a tiny sliver of the galaxy in one lifetime. The Milky Way is around 100,000 light years across. Even if you manage a miracle ship and travel 20, 30, maybe 40 light years before you die, you've still only crossed a fraction of a percent of the galaxy's diameter. The universe is too big, light is too fast, and human lives are too short. That is just the mismatch you are born into. But that doesn't make your lifetime less meaningful. It makes every mile you do travel more extreme. Think about what small means here. 250 miles to orbit is tiny on a cosmic map, but it's completely insane for an ape that evolved to walk a few miles a day. 240,000 miles to the moon is nothing next to trillions, but it is 250,000 miles away from the only world your species has ever known. Tens of millions of miles to Mars are a rounding error between stars, but for you, that is a journey where the sunlight is weaker, the sky is different, and Earth is just another bright dot. You are a primate with soft bones and a fragile brain, riding machines that throw fire hard enough to shake a planet, climbing onto towers powered by chemistry and maybe one day fusion, and aiming them into a void measured in trillions of miles. In one lifetime, you will not roam the galaxy, you will not tour 100 star systems, but you do get something just as rare. You're alive at the exact moment your species is learning how to take the first real steps. You live at the hinge point between stuck on one planet and starting to move out. So when you ask, how far can I really go? The strict answer is, physically not very far, but statistically, compared to the last few billion years, any trip off Earth at all is already off the charts. Orbit is extreme, the moon is extreme, Mars is extreme. Anything beyond that is almost absurd. And if you ever do ride one of those ships, even for a few hundred miles up, you're already part of the tiny fraction of your species that actually tested the size of the universe with their own body. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.